Hello everyone, I'm back with another video about optimization. This video is about scalarization techniques, which is a way to solve a multi-objective optimization problem. A multi-objective optimization problem is an optimization problem which its objective function is included of several functions. It means in order to solve this problem, we should optimize the value of each of this component of our optimization objective function. But actually, in real world, it is really too expensive to solve this original multi-objective optimization problem. And so we should use another method as a replacement to solve a simplification of this original problem. We should, but first of all, before simplifying our original problem, think about two questions. The first of all, does the optimization of scalarized problems result in efficient point? Is an efficient point for our objective function? Can we obtain or efficient points or vectors on Pareto front by changing parameters of the scalarization function or constraint? So after answering these two questions, we can choose the method of scalarization to solve our optimization problem. First, we need a definition, and it is a feasible solution. It's called efficient, weakly efficient, or properly efficient of our solution of our multi-objective optimization problem, which is described here. And if y equal to fx is respectively minimal, weakly minimal, or properly minimal element of our objective function. We have here six different approaches in scalarization methods, and I will explain really briefly about each one and mention their features. The first one is here weighted sum scalarization method. In this method, we change our original multi-objective scalarization method to this problem. And this is here a combination of our each optimization objective function, and WI is weighted which we want to allocate each objective function, and we want to solve this problem. As we see, we do not add any extra condition to this problem, which is one important feature of this method. The most important feature of weighted sum scalarization method can be described here. The first one is that this method can be applied to any close-pointed convex con C, and the other one is that boundedness from below for our objective space is not an essential condition for our problem, although it can be possible that we may have not a final optimal solution for some weights. And another feature is the convexity condition, which is essential for this method. And the other one is that as a decision maker's preference, we will consider the weights for our objectives, but the reference point information will not be taken into account. And the last one, as I mentioned before, is this method does not use additional constraint. Next method, which I will explain about that, is Epsilon constraint method. In this method, we Our goal is to optimize the value of objective function fk, which is at the first step selected, and we have this assumption, which you can read here, and we convert our optimization problem to this problem with an additional condition. And we should optimize this function. The most important features of this function is that, first of all, it can be applied on any objective function which its order cone is equal to r plus n, and boundedness from below is not an essential condition for this method, and also this method does not require convexity condition. And this method generates a weakly efficient solution but does not provide conditions for generating properly efficient solution. Uh, as a decision maker's preference, such as weights or reference point, are not taken into account in this method, and the problem size increases due to adding this condition to the problem.
The next method that I want to explain about that is Benson's scalarization method. And the idea of this method is, first of all, choose an initial visible solution, which we will call it x0, and define a new variable li, which is this difference, and we want to solve this optimization problem and maximize this summation, which is a replacement for our original multi-objective function. In this method, we have these features. It can be applied to any optimization problem which its ordering cone is on r plus n, and although the boundedness is not an official condition for this method, but it may not be easy to find a successful initial solution for this problem. And this method does not require convexity assumption, and the method provides necessary and sufficient conditions for efficient solution, but will not guarantee to produce this properly efficient solution. And another feature is that preference of decision makers like weights and reference point are not taken into account, and due to adding this condition to our problem, the size will be increased. And next method is weighted Chebyshev scalarization method, and in this method we need two definition. The first one is an ideal point, which is z star I, and this minimum value of our objective function, and we define this weights to have minimum value of this difference, and this is defined as maximum value of this value of our objective function, and also our minimum value. And so we defined here the replacement of our original multi-objective optimization problem as this minimization problem under this adding condition, and our feature will be as follows. The first one is that this method can be applied on a problem when the ordering cone is in Rn plus, and we need a condition be satisfied, which is be bounded from below, and convexity is not necessary condition, and this method guarantees a weakly efficient solution but does not provide guarantee to produce this its properly efficient solution. And also this method take into account decision makers preference like weights and objectives. um, and also the method uses n-dimensional function constraint, which is that, and this condition may complicate the solution process. So we should be a little bit careful with this approach. And the next one is Pascoletti-Serafini scalarization method, and in this method, which can be interpreted as a scalar problem, can be defined as minimization the value of t, and t is defined in this linear equation. And the feature of the in this method can be like this, that this method can be applied on arbitrary ordering cone, and boundedness from below is not an essential condition, and does not require to be convex also. And any solution of Pascoletti-Serafini scalar problem is at least weakly efficient. It is too important. And this method does not take into account the information on weights. And also the method uses additional function constraint, as we see, and it can complicate the solution process. And this method can be used for every ordering cone. It is too important, and we should keep in mind. And the last method which I want to mention is conic scalarization method. And in this method, the idea behind it is very simple, and we want to choose a preference parameter which consists of this weight and reference point determined an augmentation parameter such this value is in this space. And we have this minimization problem under these conditions, and it cannot be too easy to solve. And this method also can be applied on arbitrary ordering cone, and boundedness from below is not essential condition. However, for some parameter, the corresponding scalar problem may be unbounded. And so we may be careful about boundedness. And this problem does not require convexity condition, and also always yields efficient, weakly efficient, or probably efficient solution if the corresponding scalar problem has a finite solution. It is really important feature because insofar that we can solve this problem, we may have a really good solution. The preference and reference point of decision maker is taken into account, taken on consideration, and this method does not use neither additional constraint and not additional decision makers, but we should be aware of this value which should satisfy these conditions. And this method is a generalization of weighted sum, Benson's and Pascoletti-Serafini scalarization method. So that was a really brief introduction of a scalarization method to solve multi-objective functions. Please let me know if the video was helpful or you have other questions. Thank you. Bye.